So you guys haven't really done too much with probability yet. It used to be in 9th grade, but then sadly they took it out of 9th grade. I used to love teaching this in 9th grade. Huh?
So we did learn it.
I get to teach it now, yes.
We did learn it.
We did not do probability in 9th grade. True story. So, with probability, we attempt to assign a number to how likely an event is to occur. That's what we're looking for. It's how likely is something to occur. And that's what the probability tells you. So, some definitions we have here. An experiment is just some process that occurs with well-defined outcomes. So like an experiment could be flipping a coin, or rolling a die, or finding out how many blonde-haired people are in our school. Those would all be experiments. An outcome is a result from a single trial of the experiment. So let's say I'm flipping my coin, an outcome could be heads, or another outcome could be tails. So your outcome is just what could you possibly get. An event is a collection of one or more outcomes. And then a sample space is a collection of all of the possible outcomes in an experiment. So let's take a look at our spinner we have over here. What is the outcome of this actual spinner right now? 1, because our little arrow guy is over in the little 1 section. But what are all of the possible outcomes we could get? 1, 2, 3, 4, 5. So our sample space is 1, 2, 3, 4, 5, because that's what you could possibly get. But our actual outcome is the 1. That's how we define those. So the basic definition of probability is this. And people look at that and they're like, oh my God, what does that mean? So all that means is this big capital P means probability. So this is the probability of an experiment happening, where it would be your outcome over your sample space. That's what that's basically saying there. So our question number 3 there says, in the above experiment, what is the probability I land on a 5? Well, how many 5s do we have? 1 out of how many sections? 5. So our probability of landing on a 5 would be 1 out of 5, 1/5. What's the probability I do not land on a 5? 4 out of 5, because there's 4 of them that are not 5s out of all 5 sections. We call these two things, getting a 5 and not getting a 5, are called complements, because they're basically the opposites of each other. What happens with your complements is if you add their probabilities together, it equals 1 whole. So 1/5 the probability of getting a 5 plus 4/5 the probability of not getting a 5 would give us a 1. So number 5, what is the probability I land on an even number? 2/5. I got 2 even numbers out there out of 5. What is the probability that I land on a 3 or a 5? That would be 2 out of 5. Now, without really thinking about it, what you guys did is whenever you see the word or in probability, that means you're actually adding things together. Now, in this example, it was really easy to add them together. You just did the 3, the 5, 1 plus 1 gave you your 2 out of 5. If we actually had to add them, though, what you're doing is 1/5, which is the probability of getting a 3, plus 1/5, which is your probability of getting a 5. Add those together, that's where we get our 2/5 from. 7, the probability we land on a 6. Do we have any 6s there? So that would be a 0. Yes. No. Whenever your probability is 0, we call that an impossible event. That's never going to happen. And then question 8, if I spin the spinner twice, what are the chances that I land on a 3 twice in a row? So what we're looking for here is the probability of getting a 3 and then another 3. So we're looking for the probability of a 3 and a 3. So in probability, the word and means we're going to multiply, or you add, and we multiply. So what's the probability of getting a 3? 1 out of 5. And that's going to be times. What's the probability of getting 3 again? 1 out of 5. Because we're still using the spinner up above. There's 1 3 out of all 5 sections. So multiply your tops. 1 times 1. 5 times 5. So it's 1 out of 25. Chance of getting 2 3s in a row. Questions so far?
No.
Okay. So next up is our counting principle. Sometimes they ask you questions where all they want to know is what is the sample space, or how many elements are in your sample space. So your counting principle does just that. Counting principle goes with your sample space. So sometimes our sample space is rather large, and you don't want to sit there and actually write out everything that would be in the sample space. It just takes up way too much room. So what you do is you take all of your options and you just multiply them together. So like for our first example here, we have Ellen, who has 4 pairs of pants, 3 shirts, and 3 scarves that all match. How many outfits that include pants, a shirt, and a scarf can she put together? So the way we figure that out is we have 4 pairs of pants times her 3 shirts times her 3 scarves. So 4 times 3 times 3 gives us, so she has 36 different outfits she can put together with those items. So another example, we have a delicatessen serves sandwiches on rye, white, or rolls. And then they have 8 different sandwich fillings. And then customers have a choice of lettuce or no lettuce. So they want to know how many different sandwiches can be assembled. Yep, so it's 3 choices of bread times the 8 sandwich fillings times the choice of lettuce or no lettuce. They have 2 options there. So 3 times 8 times 2 gives us 48. So that's just how you figure out your sample space. You just multiply out all your options. That tells you how many different outcomes are in your sample space there. And then people usually develop contests of who can eat all 48 different sandwich choices. Okay, experimental probability. We're going to go through and there's going to be a whole bunch of different types of probability that we have within here. You don't really need to know the names of them. A lot of times just reading through the problem, you know which kind of probability you need to do. So experimental probability just means they've done an experiment. Like this over here, they were asking who prefers what kind of sodas, and they gave them 3 brands. So you just have to figure out your probability based on what they've already done. So A, find the empirical probability that a person selected at random would prefer soda B. So then we look over here, how many preferred soda B? 24 of them did, out of how many people total? 53. And that's it. That's the empirical probability of people who preferred soda B. 24 out of 53. So then B here, find the empirical probability that a person selected at random would not prefer soda A. So if they do not prefer soda A, that means they liked what? B or C. So let's add those together. 24 plus 11, 35 out of. This time they wanted it to 2 decimal places, so you got to use your calculator and divide. Hmm? 0.66. That's all it is. You're given a table. Find your probability based off your table. Okay, moving on to our two-way tables. Two-way tables we have done in 9th grade. I know for a fact you did them in 9th grade because I wrote the notes for that day. So I know you guys did it. So two-way tables is categorical data, not numerical data. And it's broken down into categories and counts are recorded. So it's not something you can measure. It's not like heights of people or size of their feet or averages in math class. It's other things, like for example here, male, female, so gender, what was their preference, what kind of vehicle did they like. They'll do ones on eye colors, what's your favorite kind of food, what's your favorite kind of color. It's those kind of numbers that they're data that they're looking at.
This one seems like an unfair survey.
Why?
They ask more people than males, so they're statistically showing that more females select SUVs. They ask more females than they do results.
And now you're getting a little more into the statistics aspects than the probability.
That's kind of fixed.
So we have here a survey asked if you could have a new vehicle, would you want an SUV or a sports car? The results of the survey have been summarized and placed into this two-way frequency table. Use the table to answer each of the questions below. So they had 2 variables they were looking at. They were looking at gender, and then they were up here looking at what kind of car did they prefer. So first thing we need to do is fill in our totals. So adding down, what would be our total for SUVs? 137. What's our sports cars? 84. Add those 2 together, what do we get? 221. So then add up your males, 2 plus 39. And then our females, 180. Do those also add to give you 221? Yes, there we go. So we know we did our table correctly. Everything adds up. So these next 4 questions, we're rounding all of our answers to the nearest hundredth. What percent of the survey takers were female? Now, because they said of the survey takers, that means it's going to be out of the 221. So how many of them were female? 180. If you look at your female, our total for female was 180. So let's do 180 divided by our 221 and then times 100. But we want it to the nearest 100, so it's 81 point. Should get 0.45. Now our next one though, question 2, it says what is the probability that a male taking the survey will pick a sports car? So because they said that a male taking the survey, that means this probability is going to be out of 41 because we had 41 total males. I divided and then times 100. So how many of them chose a sports car? 39. So let's divide that. No, this one's probability, not percent. So that one would be 0.95. You gotta be careful. They switch between percent and probability all the time. 3, what percent of individuals taking the survey were females choosing a sports car? So this is going to be out of our 221 because it said of individuals taking the survey. And they want females choosing a sports car. How many females chose a sports car? 45 did. So 45 out of our 221 gives us what? 20.36%. last one, what percent of those who chose the SUV were males? So we're looking only at those who chose the SUV. So how many people chose an SUV total? 137. Of those 137, how many were males?
1.46%.
Oh, you're one step ahead of me. I was looking for the 2 for now. So 2 out of the 137, yes, would be 1.46%. Questions on that table so far? So you just got to be able to read the problems to figure out what you're doing the questions out of. So now example 2, we have to go ahead and fill in our table. So for your table, this bottom here, this one's always your total. This column over here is always your other total. I always fill those in first. So then we have in a class of 20 students, 5 boys and 7 girls like chocolate ice cream, 6 boys like vanilla ice cream. They want us to organize this data. So what are the 2 things we're talking about here?
Boys and girls and ice cream.
Yep, boys and girls. So boys and girls. And then chocolate or vanilla. So let's fill in what we know. We know 5 boys chose chocolate ice cream. And we know 7 girls also chose chocolate ice cream. And then 6 boys chose vanilla ice cream. And we had a total of 20 students in the class. So we know that that total over there in the bottom right should be 20. So let's fill in our missing numbers. 5 plus 7 gives us 12. So what number should be here to give us 20? 8. So then what number should go here to give us 8? 2. And then we'll add across. 5 plus 6 gives me 11. 7 plus 2 gives me 9. 11 plus 9 gives me 20. So it all adds up. We're all good. So let's answer our 2 questions down here. Based on this survey, what ice cream flavor was most popular among students? Explain your answer. So which one was most popular? Chocolate. How do we know it was chocolate? Because more kids picked it, right? You could go through and figure out your probability of chocolate versus vanilla, and you could use your probabilities as part of your explanation also. B, a student is picked at random. If this person is a girl, do you think she would prefer vanilla, and why? So if I randomly pick a girl, do you think she'd prefer chocolate or vanilla? Chocolate, why? Because yeah, again, more girls pick chocolate. So do you think she would prefer vanilla? No. Because more girls picked chocolate. How are we doing so far?
Great.
I'm good.
Chalky milk.
Okay. So next we're going to talk about making a hypothetical 1000 table. So it's usually easier to interpret counts rather than percents or probabilities. So you can make a frequency table using either 100 or 1,000. You could even use 10,000 if you wanted to as your total, as long as it's a power of 10. Any power of 10. The table you make is called a hypothetical table. So if you go through and you make a hypothetical table, when you go to answer your questions afterwards, you can't make definitive statements. You have to make statements like, I think it would be this because of the probability, or I feel as though it would be this for this reason. You can't definitively say, yes, they're going to have more ice cream or anything like that. It has to be an I think or I feel, because it's just a hypothetical table. So here we have health officials in Milwaukee. We're concerned about teenagers with asthma. So in a local research study, researchers collected data on the incidence of asthma among students in a Milwaukee public high school. Students completed a survey that was used to begin the research, and based on the survey, the probability of a random selected student at the high school having asthma was 0.193. Students were also asked if they had at least one family member living in their home who smoked. So the probability of a random student having at least one member in their household who smoked was 0.421. And then the probability that a random selected student with asthma has a household member who smokes was 0.120. So what we're going to do is we're going to make our hypothetical 1,000 table. So our total over here is going to be 1,000. So now we're going to take these probabilities that they gave us, and we're going to figure them out. So a student selected having asthma was 0.193. So I want you to take that number and multiply it 1,000. What do we get? So students with asthma, there was 193. Our next one was a student having at least one member in their household who smoked, was 0.421. So multiply that by 1,000, what do we get? So household member who smokes is 421. And then a student with asthma who has somebody who smokes is 0.120. So multiply that times 1,000, what do we get? $120. So asthma and smokes, 120 goes there. So now we should be able to fill in the rest of our numbers. What's 1,000 minus 193? That's 807. 421 minus 120, 301. Now we'll get our last column. 193 minus 120, 73. 807 minus 301, 506. And then our last box here, 579. Because 421 minus 120 gave me my 301. All right, so a randomly selected student has asthma. What is the probability the student has a household member who smokes? So looking at the students who have asthma means this is out of 193. How many of those 193 have somebody who smokes at home? 120. Now we have to keep things consistent. They gave us our probability as decimals. We have to turn these ones into decimals. So 120 divided by 193, what does that give us? 0.622. We'll go to three numbers because they always gave us three numbers up there. So a randomly selected student does not have asthma. What is the probability he or she has a household member who smokes? So how many students total do not have asthma? 807. How many of those have somebody who smokes at home? 301. So 301 divided by 807. What do we get? 0.373. next one, a randomly selected student has a household member who smokes. What is the probability this student has asthma? So how many households total have somebody who smokes? So this is out of 421. Of that 421, how many of them have asthma? 120. .285. Now, the tricky part with our probabilities are these questions here. Do you think that whether or not a student has asthma is related to whether or not the student has at least one family member who smokes? Explain your answer. When I did this problem, I got one answer. And then I went over to Mrs. Stevens to check my answer keys, because that's what we always do. And she had a completely different answer. But the thing was, neither of us were wrong, because our explanations were actually valid. So with these questions, there's never really a right or wrong answer. It's just kind of, how do you see the problem? So let's see what you guys come up with. Do you think that whether or not a student has asthma is related to whether or not they have somebody at home who smokes? Yes or no? Got some yeses. Okay, if you have yes, you got to come up with a why.
Shows that most people with asthma has at least one family member smoking.
Okay,
Look at the probability we show.
that's one way you could go about it.
So it'll be correct.
That would work. I'm not saying it's correct, because there's lots of different answers. I went with no. Is anybody out there else thinking no? A couple of people. My reason for going with no is if you look at the people with asthma out of the people who have someone who smokes at home, the probability is only 0.285. So if we turn that into a percentage, that's approximately 29%. That's not very high. 50% is halfway there. 29%, that's not very high. So I said no. Ms. Stevens had said yes, because the probability that you have somebody at home who smokes when you already have asthma was higher. So she went with that number. So really, again, there's no right or wrong answer. It's just all about how you look at the problem. So you can write whatever you want here. I'm going to give you a minute. All right, let's look at our last one down here. Does having a household member who smokes cause a student to develop asthma? Paul,
I'm going to say answer.
go for it.
I'm going to say no, because there is no data given in the chart that would lead to. That's not what the data is covering. Data is covering people who already have asthma. Therefore, to determine if it causes it, it doesn't include the
Yes.
Yes, that's right.
What? Well, yeah, another reason you could say no is how many of these people live with somebody who smokes who doesn't even have asthma? It doesn't cause it. This goes back to some words that we're going to see if you remember. No, because even though there is a correlation, you guys remember that word? Can anybody tell me what it actually means?
A connection, like a relationship.
Yeah, there's a connection, there's a relationship there. So even though there is correlation, it does not mean causation. Meaning it doesn't cause it to happen. Because if it did, then everybody who lives with somebody who smokes would have asthma. But they do not. So even though there is a correlation there, there is a connection there, it does not mean causation. So our last thing here is our conditional probability. And when the probability of one event occurring changes based on other events occurring, then we say that's conditional probability. Your probability depends on something else that's happening there. So here we have a table talking about genders, male, female. Are they going to college? Are they not going to college? So they want us to determine these probabilities here. So the probability, that's what the P stands for, probability that it's a female student. So how many females answered our survey? 22 out of how many total? 52. So the probability that the student is female is 22 out of 52. Probability that the student is going to college. You don't have to. So now this next one, this one's a conditional probability. This is the probability that a student is going to college given that she is female. So this vertical bar right here means given that. I wrote that down there for you. So what that does is it changes it from being out of all 52 people, it's now just out of the female students. So this is out of 22 now. So how many of those 22 females are going to college? 13 of them. So that bar changes what you're looking at. Nope, there's 22 total females. My female is total 22.
Oh, okay.
13 of them are going to college. Now, once again, they do have a more formal definition for it, which is this right here. So that stands for the probability of A given B. So whatever event A was, in this case, was going to college, given event B, which is being female. This little symbol here, we're going to talk more about next class, means and. So the probability of them going to college and being female. We did that. That was our 13. Over the probability of them being the one thing. So in this case, probability of going to college and being female was 13 out of 52. And so then the probability of being female was 22 out of 52. But we can't have a fraction over a fraction. That's just not allowed. So how do we fix that? Keep, change, flip. Well, you threw me off because then I started thinking about KFC, and now I'm like, I'm hungry. I want KFC now. Yeah, I know, but it's so good. So what happens with our 52s? 52s cancel. And we get 13 out of 22, which is what we said up above was our probability. So we had done that formula, only a little simpler there. So next one, they want to know, is it more likely that the person picked at random will be going to college given they are male, or that the person will be male given that they are going to college? Which I know sounds like the exact same thing, but it actually is not the exact same thing. I promise you that. So, for the first one, how many males total? 30. Because it said going to college given that they are male, so that means it's out of the males now, so that's going to be 30. How many of them are going to college? 16. So let's divide that. What do we get?
0.53 repeating.
Okay. So now let's flip it. Probability that they are male given that they are going to college. So how many people total are going to college? 29. And again, how many of them are males? So let's divide that one. We get point what? So which one is more likely? Neither of them, really. Aren't they pretty much the same? Yeah. So, neither. They are pretty much...
Yeah, but no, one is higher. You can technically
those are pretty much the exact same thing.